Over the past year, I've been investigating the climate of the Younger Dryas. The Younger Dryas occurred from roughly 13,000 to 11,700 years ago. It's a recent example of abrupt climate change and is characterized by a rapid transition into and out of cool and dry conditions centered in the North Atlantic. Greenland ice cores record a change of 5 to 10 degrees Celsius in a few decades or less at its termination. Currently, there is some evidence that suggests much of the cooling occurred in the winter season and not in the summer. These seasonal temperature differences are referred to as seasonality. The degree of seasonal shifts are quite important to understand for future climate and when synthesizing proxy-based records of past climate change. New records are also valuable, especially when they are from different regions and proxies. The schematic shown here demonstrates how I use bug parts and mosses from lake mud to reconstruct past climate change. Climate change drivers, like greenhouse gases and solar cycles, alter Earth's temperature. These changes in temperature then, in turn, alter the oxygen isotope chemistry of precipitation, which ends up in lakes as lake water. Fortunately for me, bugs, like chironomid larvae, and aquatic mosses use the water as their chemical source as they grow. Because of this, they record a snapshot of water chemistry and are preserved in the sediment for their eventual rediscovery. Therefore, sampling and measuring the chemistry of chironomid head capsules and mosses from sediment cores allows me to reconstruct past lake water and climate. Over the past year, I've been sampling mosses and chironomids from South Greenland lake sediments to generate a new climate record. The chironomids likely reflect an annual signal, but the mosses may provide a new way that we can reconstruct multiple climatic seasons. We have some evidence of modern mosses in the Arctic showing seasonal growth patterns. On the left, you can see the cold season, where there are fewer leaves per centimeter of moss stem than on the right in the warm season. By finding and isolating moss strands, I can measure their isotopic values to see if there's a difference in the cold and warm seasons of moss growth. If clear differences between the strands are present, I hope to develop this into a useful lake sediment-based proxy for seasonality. I've just finished sampling the mosses and chironomids, and I'm currently preparing them for measurement on the IRMS.